Good morning to all. Now this session we are going to discuss Fourier sine transformations, Fourier cosine transformations. In the previous one we concluded Fourier transformations. Okay. Now let us start. Now in this session Fourier sine transforms and Fourier cosine transforms. These things now we are going to discuss. So for Fourier sine transformation, simply we write f of s. For Fourier cosine transformation, we write like this. Suffixes. S for sine, C for cosine. Now before going for this one, we have to go for scaling property. Scaling property. If Fourier sine transformation of any given signal that is equal to f of s. Look at here, if you write the signal s, symbol s, here also you are supposed to make it symbol s. That s represents sine transformation. If Fourier sine transformation of f of t equal to f of s by s, then Fourier sine transformation of f of at, because this is scaling, here it multiplies, there it divides, that is 1 by a f of s into as. Okay, similarly f of s into f of t by a, that is equal to a times f of s of, sorry, this becomes division, not as, f of s of s by a. Now this becomes a of s. So here the constant, here it multiplies, there it divides. Here it divides, there it multiplies. The same concept is applicable to cosine too, cosine transformation also. If the Fourier cosine transformation of a signal f of t that equal to f of s cosine transformation, then Fourier cosine transformation of, here you multiply, there it divides, that becomes 1 by a Fourier cosine transformation of s by a. And Fourier cosine transformation, if you divide by a constant, there it multiplies. This will become Fourier cosine transformation of a of s. Now look at the scaling property. That means what? The scaling property is applicable to Fourier sine transformation and also as well as Fourier cosine transformation. In that means the scaling property that is same. The scaling property principle is same whether you discuss Fourier transforms, whether you discuss Fourier sine transformation, whether you discuss Fourier cosine transformation. For all these three, now this principle is same. That principle is called scaling property. Now we are going to discussing Fourier sine transforms and Fourier cosine transforms. Again I am remembering you, we are discussing transforms. Already integral part is over as a part 1. Integral part means we have two integrals. Transform part means we are having only single integral, make it a point. Now this is very important concept. Okay, so these are scaling property and Fourier sine transformation and Fourier cosine transformation. Understanding? Now before entering Fourier sine and cosine transformations, there are two important formula, very important formula, that is integral. Look at, limits are 0 to infinity, not 0 to infinity e power minus at sine bt dt is equal to b by a square plus b square. Very, very important. Second, integral 0 to infinity e power minus at into cos bt dt its value is equal to a by a square plus b square. These two are very important formula. Very important formula, because just look at, in both of the cases 0 to infinity, 0 to infinity, e power minus at, e power minus at, but here sin bt, here cosine bt. Whenever there is a sin bt, the output will be coefficient of sine will come into the picture. In case of cos, coefficient of e exponential function will come into picture. In both the cases, the denominator is a square plus b square. Understanding? This is very important concept. For example, just look at, for example, find Fourier sine transformation of Fourier sine transformation. Understanding? This is very important concept. Got it? No. The next one I will be making. Now, these two are very important. Now, first one, find Fourier sine and Fourier cosine transformations of 2 e power minus 5t plus 5 into e power minus 2t. First one. Understanding? We have to find Fourier sine transformation and Fourier cosine transformation of this one. These two. Firstly, I am finding Fourier sine transformation. Now, Fourier sine transformation of any function, any signal, f of t equal to integral 0 to infinity. What is that signal? F of t. Because of sine, it comes only sine term. S of t into dt. The domain will be in terms of f of s. Now here, what is f of t? Here the given f of t equal to 2 times e power minus 5t plus 5 times e power minus 2t. Therefore, Fourier sine transformation of f of t is equal to integral 0 to infinity of 2 e power minus 5t plus 5 times e power minus 2t dt. Now split the integral. Constant 2 times e power 0 to infinity e power minus 5t into which term? E power minus t into, this is sine, therefore sine st dt. Now into sine st dt plus second constant 5 0 to infinity e power minus 2t into sine st dt. Understanding? Now we are using the principle e power minus at into sine st. Constant into, in this case, constant will come out, that is s by s square plus b square means what? 5 square, 25 plus 5 times, here it is s by, what we get? S square plus 4. Plus 4. Understanding? So here both are sine, therefore s will come out. You can take s as common. So s as common, you will get 2 by s square plus 25 plus 5 by s square plus 4. You can keep it like this, otherwise you can simplify this one. If you simplify 7s square plus 125 plus 8, 133. 133 by s square plus 4 into s square plus 25 into the value is s. This is the Fourier sine transformation of that given signal. If you go for Fourier cosine transformation of the signal f of t, now directly just I am going for, already we done like this, directly just we are going for, in place of sin st, we will get cos st. I am going for the direct step. that is equal to 2 times integral 0 to infinity e power minus 5t into cos st dt plus 5 times integral 0 to infinity e power minus 2t into cos st into dt. Now this is 2 times e power minus at into cos bt. Whenever there is cos, a coefficient of exponential will come out, s square by 25. Next, plus coefficient 5 into 2 by s square plus 25. In both the cases, you can make it 10 as common. There is no question of s because of cos. This is becoming as s square plus 25 plus 1 by s square plus, this is cos 2t, not 25, this is 4, s square plus 4. This is s square by 4. You can keep like this, or if you want to make it, you can make it 10 times 2s square plus 29 by s square plus 4 into s square plus 25 if you go for LCM of these two. Now just look at. This is Fourier sine transformation of a given signal. First you go for the formula. The second one, look at this one, only just we made the simplification on the basis of what? Only two formulae. If 0 to infinity e power minus at sine bt dt, then directly just we go for the formula of b by a square plus b square. Just we substituted. And also integral 0 to infinity e power minus at and cos bt dt. This value is equal to a by a square plus b square only. Based upon this one, just look at here, based upon e power minus at sin bt. In case of b, s is here, s by s square plus 25, s by s square plus 4. In both the fractions, s is the common. We make it s, then 2 by this, simplification. Now based upon this one, just I went for direct step for this one. Up to this one same. Just in place of sin st, we got cos st only. So because of cos, only coefficient of exponential will come out, not coefficient of cos. So here 5 by s square plus 25. Here s square by s square plus 4 only. In this one 10 is common. You can keep like this, or better to go for another step and make two fractions into a single fraction like this. So this is the output of this one. So now just a signal, we found Fourier sine transformation of this signal, Fourier cosine transformation of that signal. Thank you.